Hi, my name is Oliver, and today I'm going to be analysing the voltage and current characteristics of LED, PIN and Zener diodes. The aim of Experiment 1 is to use various software including Microsoft Excel and MATLAB to come up with an analytic approach of expressing IV curves for light emitting diodes, a PIN diode and a Zener diode. This will allow the theoretical and physical threshold voltages of each diode to be compared, as well as provide insight to the way various diodes affect the flow of alternating current. Furthermore, sources of error can be identified at various voltages for each diode. The characteristics for each diode were monitored continuously on a cathode ray oscilloscope by setting up a circuit using a function generator to generate a time-dependent voltage. To accurately measure the voltage drop across the 100 ohm resistor, a differential amplifier was used to minimize current leakage. A diode allows current to only pass through one direction in a circuit. It consists of two electrodes which essentially act as an on and off switch. It turns out that when the depletion region formed at a PN junction is subjected to an external voltage source, the potential difference across the region varies. If the P-type material is connected to a positive terminal and N-type material is connected to a negative terminal, a forward bias is created, allowing current to flow. However, it's important to note that in order for this current to flow, the input voltage must be larger than the potential difference across the depletion region. Contrastingly, when the power supply is reversed in polarity, a reverse bias is created, causing the depletion region to expand. This prevents the flow of current. The Shockley equation shows that beyond the threshold voltage, we observe an exponential rise in current. Realistically, it's actually found that the diodes have a certain breakdown voltage, which is the maximum reverse voltage that can be applied before the device becomes damaged. There exist many different types of diodes with varying physical properties. A light-emitting diode, otherwise known as an LED, begins to emit photons and illuminate once a large enough voltage allows electrons to cross the depletion region. This value is known as the threshold voltage and varies depending on the color LED used due to the frequency of visible light. A PIN diode is a diode with an undoped intrinsic semiconductor region placed between the PN junction. This results in a wider depletion region than a standard diode, increasing the breakdown voltage of the device. Another type of diode is a Zener diode, which is designed to have a precise breakdown voltage that can assist in voltage regulation. Unlike most diodes, the Zener diodes allow current to flow backwards when a specified reverse voltage is reached. This is known as the Zener voltage. First, the provided raw data containing voltages from the two oscilloscope channels were imported into MATLAB. The voltages from channel 2 were then converted into currents by simply dividing each voltage by the 100 ohm resistor, which provides the current flowing through the diode. The find groups function in MATLAB was then used to split up all the current readings for each individual voltage and store these as arrays. The split apply function then applied mean and standard deviation functions on each block of currents. This provided an average current reading for each given voltage with a respective standard deviation. The IV curve could then be plotted, containing the mean current as a function of voltage for each diode. This was easier to visualize by plotting the larger increments of voltages so the data points and error bars were more spaced out. Using these plots, the threshold voltages of each diode could be identified by observing where current can no longer flow. Additionally, voltages with large deviations of current can now be identified. Unfortunately, due to the range of bugs in my MATLAB code, I wasn't able to take the standard deviation and averages for each voltage, and this limits my evaluating error bars. So, beginning with the IV curve for the red LED, we can observe that at approximately 2 volts, the threshold voltage is reached. And beyond this voltage, we observe an exponential increase in current, which agrees with the theoretical Shockley equation. This same logic is applied to the white LED, where we can see that at about 2.5 volts, the threshold voltage is reached. When these threshold voltages are reached for both LEDs, they would begin to illuminate and get brighter with increased voltage. Since the intensity of light being emitted is proportional to the amount of photon-electron interactions, an increase of current causes these interactions to take place faster, and so our results agree with this theory. As expected, the PIN diode has a similar shaped IV curve to the other two LEDs. The PIN diode recorded a threshold voltage of approximately 0.8 volts. For the Zener diode, it can be observed that the Zener breakdown region begins at negative 0.6 volts and the forward bias region occurs at 0.7 volts. As expected, the IV characteristic facilitates the flow of current below and above these respective voltage values. For the red LED, a well-defined voltage drop of approximately 1.2 volts occurs at every half cycle whilst in forward bias. Additionally, we see that during reverse bias, the voltage across the red LED drops down to a value smaller than negative 0.1 volts. This agrees to what was theoretically predicted, which was that LEDs should only provide output for every positive half cycle and act as an open circuit when current flows the opposite way. This was also the case for the white LED, where we observe a voltage pulse every half cycle. This half cycle effect is also evident for the PIN diode. Here we can observe that the PIN diode is a poorer rectifier than the LED diodes since the voltage peaks across the diode haven't dropped as much. And finally, for the Zener diode, we observe current flow in both forward and reverse bias, as expected. It's important to point out that for all four of these diagrams, the results aren't exactly perfect. For example, with the Zener diode, theoretical predictions say that we should expect a perfectly sinusoidal path, but clearly it's not exactly sinusoidal. A reason for this might be due to the fact that the laboratory temperature, whilst being conducted, was not perfectly the same, and as outlined by the Schokling equation, any fluctuations in temperature will affect the current. With a quick calculation, we can estimate the theoretical energy required for electrons to jump across the bandgap. Since the wavelength of red visible light is about 650 nanometers, we can sub this into the above equations and find that the energy needed to cross the gap is 1.91 volts. The experimental threshold voltage was found to be just under 2 volts, which is relatively close to the estimated theoretical value. If the polarity of the diode used in this experiment was switched, the IV curve would have the same shape, but be flipped laterally, since the anode and cathode will switch sides. Since the source voltage is AC, it will essentially have the same effect on the overall circuit. One way to improve this experiment is to use a more advanced oscilloscope with smaller time steps to gather more data points. This means that the average currents used for each voltage are improved since the weight of any outliers are reduced. Another improvement would be to minimize fluctuations in temperature, since Schokling's equation states that the current intensity is dependent on temperature. Diodes are significant because they're used to control and regulate all electrical devices we use today. Thank you for watching this presentation.